All right, so now I want to kind of talk a little bit more about the other trigonometric graphs, the sine, cosine, and tangent, and basically kind of take a look at what they represent. So, in the previous warm-up, we just kind of looked at, the y equals sine of x, and we related to, f of theta equals, sine of theta. And now, again, you could use, we can write this in terms of an equation or a function, and we're going to kind of go back and forth. But the main thing I wanted to do is just kind of also relate this to our function notation. And, if we just have a random function here, let's go, f of x, right? Well, we can apply these transformations. F of x is equal to a times f of b times x minus c plus d. And if you remember in our unit on functions, we talked about what a, b, c, and d basically do to our function, or sometimes we used h and k, but a, remember, was like your vertical stretch of the graph. It also was a reflection about the x-axis when it was less than 0. B was the horizontal stretch or compression of the graph. It was also the reflection of the y-axis when it was negative. C was your phase shift to the right and to the left, and just remember, not your phase shift, that was it. Yeah, your horizontal shift to the right and to the left. And again, remember, it's the opposite of C. So if it's -1, you're shifting 1 to the right. And then D was our vertical shift, kind of up and down. So you can see here, I have these A, B, C, and D in the exact same place. So what's important about this is the exact same things are going to apply for our trigonometric graphs. And when we have an A, B, C, and D, those are going to affect the graphs in the exact same way. So what I wanted to do is just kind of play around with these functions so you can kind of see, how these operate. So I chose the sine graph here, and I have A, B, C, and D. And basically what I did is just provided a slider. Now, one thing we talked about originally was this initial period from here to here. But as we keep on expanding out, what you guys can see is this graph is just going to keep on continuing, right? Because you can go around and around the unit circle as many times as you want. You can see this is oscillating back up and down, up and down. And that was one thing I didn't mention about the end behavior is this graph doesn't continue in one direction. It just keeps on repeating, right? Bouncing up and bouncing down. So there is no end behavior, as well as the increasing, decreasing values keep on repeating, right? A certain distance, they keep on repeating. So we'll talk a little bit more about that as well. But what I want to do is just kind of look at like how A changes, right? So as A gets larger, obviously we know that's going to be a vertical stretch. And you can see that's exactly what's happening. The graph is not moving, it's just being stretched horizontally. And then remember, if it goes to negative, now what's happening is, if it's going to be between 0 and 1, that's actually the same thing as like a vertical compression, right? And then once we get down to, obviously it can't be 0, we won't have a function, but once it gets down to negative, you can see that this is actually reflecting. And then once so it's negative between there, it's still a vertical compression. Then it gets above 1, it's a vertical stretch. And you can kind of see this motion as it gets closer and closer to 0. That's where that reflection about the x-axis comes from. So, no. Okay. So let's go ahead and let's just put this back at 1. Okay, now let's go and look at B. So B, if you recall, B is going to be your horizontal stretch and compression. So as this number gets 1, you can see that this graph is, not between 1. As it's still positive, you can see that it is being horizontally stretched, right? Because it's less than 1 between 0 and 1. You can see this graph is being horizontally stretched. But once I get greater than 1, you can see now we have a horizontal compression. And as that number keeps on getting smaller here, getting to 0, you can see what's actually happening is the graph is being reflected about the y-axis. Now, so you can see how it got reflected about this y-axis. And then obviously as it gets, I'm getting closer, you can see that compression. Now let's go and take a look at C. Remember, C is going to be our phase shift to the right. And again, what I talked about 1. Like you can see as the numbers get more and more positive, right? Now this one sometimes gets confusing, and that's why I'm going to give you some techniques to kind of understand this, because you could look at this and you can see as this graph is being shifted 1 unit, right, as to the 1, you can see that an x minus C, x minus 1, B, A is 1, B is 1, x minus 1, B is 0. Yeah, so it'd be -1. You can see the graph is actually being shifted 1 unit to 1, right? Because this would be -1. So you can see the graph is being actually shifted to the right. And then if I go negative, you can see the graph is being actually shifted to the left, because a minus and negative would actually show this as like a plus 2.1. But you can see the graph is being shifted over. So let's put that back at 0. And then we can last just see the D, which is going to be our vertical shift up and down. And I think that's kind of obvious here. Most people are okay with that. So you can just kind of see how these transformations, they're exactly the same for any trigonometric function. However, we do have some new notation, and we do have some different things to kind of discuss when we look at these. So that's what I wanted to kind of talk about these, making the relationship. I'm not going to go through, what A, B, C, and D does, because we've already talked about that for functions. However, there are some things that are important because we haven't dealt with a graph that continually repeats. And so what I want to do is just kind of go over our initial periods for the sine and cosine graph, and then understand how to find those start and ends of the initial period. So let's just go ahead and redo kind of our warm up here real quick. So the initial period for y equals sine of x. All right, and again, this is exactly basically like 1 revolution of the unit circle. This is what the graph is going to look like. So just come through there and repeat. So therefore, it repeats, starts at 0, has an x-intercept at pi, has a maximum value of 1 and a minimum value at -1. And that is basically what we call the initial period. And so that is just kind of helpful because obviously this graph repeats, right? As we keep on going around the unit circle, it's going to keep on repeating. And as we go to negative values, it's just going to keep on repeating. So the initial period for cosine of x, we didn't have time to do that for this warm up in our notes, but if you do the investigation, you can go ahead and see that this graph is going to be still at pi. So this graph is going to have the same maximum and minimum values, but it's actually going to start up here now, and it's going to look something like that. Okay, now we actually can figure out these x-intercepts, and that's going to be actually at pi halves and 3 pi halves. And if you look at the unit circle, you can see cosine is equal to 0 at those two angles. But again, it finishes at 2 pi. Okay, so one thing I wanted to kind of cover in this is obviously the transformations are from these functions. This is what we're going to base all of these operations of. So if we have a vertical stretch, that's obviously going to stretch the graph from 1 and -1, right? For sine and cosine. If we have a B, that's obviously going to be compressing or stretching it. But since the graph repeats, it's important, since that graph is repeating, like you're still going to get that compression, and that's going to like affect our frequency, but but it's just going to kind of seem like it's kind of repeating. It's kind of, it's not going to make any change as far as it does make change as far as the intercepts as well and intervals. But it just kind of, it's not just the change on the initial period. It changes for the whole function. And then obviously C and D, this is something that once we look into the same graph, like it's very important to understand what the phase shift is, because sometimes looking at a graph, it's not going to be as obvious. Like right now, we know that this graph with no transformations has x-intercepts at 0 pi, 2 pi. So when we apply a phase shift, those x-intercepts are going to change. But sometimes it's not as obvious was that a phase shift to the right or to the left? And that's where a lot of times it can get confusing. And obviously D, I think, is fairly plain and simple. So there is one thing I want to kind of talk about that I think is helpful when we're dealing with the initial period of the sine and cosine, and that is going to be the start and the end. Okay, so basically, if you have some trigonometric function, you have all these A, B, C's, and D's, and you really need to kind of understand what the initial period, like where does it start, where does it end? And if you do that, then you can understand where the transformation is, like what exactly is the, where the graph is being shifted, because sometimes looking at the graph is just not going to be enough information. So the way to do that is you can see for both of these graphs, they both start at 0. So basically what I'm going to do is take whatever values inside of my function I have. So b times theta minus c. So if I have a b minus c, I'm just going to set that equal to 0. And then basically, you're going to want to just solve for theta. And whatever theta is, that is going to be your shift. That is going to be your horizontal shift. That's going to be the new starting point for the initial period. So therefore, let's just say our new starting point ends up being at, negative pi halves. Well, then you can say that the graph has been shifted negative pi halves to the left. And then to find the end, you can see that both of these functions end at 2 pi. So we'll set up the exact same equation. And instead of just writing that, I'm just going to say solve for theta. Okay, and by doing this, again, this is just going to tell you where the new start and end. It doesn't really tell you the shift up and down. It's not going to tell you, the stretch or the compression or the reflection, but it is going to tell you where this graph is being shifted. And that's going to be helpful because sometimes not always looking at the graph is easy to identify the horizontal shift. Now the tangent graph is completely different, so I do want to kind of cover that. But before I cover that, I want to kind of talk a little bit more about the characteristics of sine and cosine. So the characteristics of sine and cosine, obviously we have an amplitude, and basically the amplitude is the half distance from the max to the minimum values. And the easy way just to find the amplitude, it's the absolute value of A. The period basically represents how long it takes the graph to repeat itself. So that's why we call this the initial period. You can see that after this graph, after the function has gone around the unit circle, it's going to start repeating, right? So the period, our initial period is 2 pi. However, if we horizontally compress that graph or horizontally stretch that graph, what you're going to see is that period is either going to be elongated or condensed. And that will make a little bit more sense, especially once we get into like solving trigonometric functions, or we'll kind of relate what the graph looks like to the solutions, but you can kind of see some things that the period can change. And so the easy way to identify the period for any function is just to take 2 pi divided by b. Obviously, the phase shift is different, is new vocabulary. So instead of saying horizontal shift, we're going to talk about the phase shift. The vertical shift is obviously d, and that's kind of the same. You can see that the domain is all real numbers. This graph just keeps on repeating and continues on and on. The range is important because obviously you can see the range of this graph. It's bounded, right? It's bounded below and it's bounded above. So it has maximum values of 1 and -1. Well, obviously, if that amplitude changes, right? So if the graph gets stretched, horizontally or compressed, or if we are vertically shifting the graph up or down, that's going to affect the range. So that's kind of some important things. And then X scale is something that I used to work on a lot when I would actually manually graph these. I don't deal with it as much anymore, basically because I don't work on graphing them to that much detail anymore. But basically the X scale is, if you guys look at the period and break it down into 4 parts, you can see there's kind of like 4 important points, right? You have the max, X-intercept, the minimum, and then back to another X-intercept. So again, intercept, minimum, intercept, maximum point. So the X scale is just a way to graph to kind of understand where the next important point is gonna occur. So as long as you know what the graph looks like and you have the X scale, you can kind of create your scale for you. But again, that's not something I use, and we're not going to really use it in this this lecture, but I just wanted to kind of provide it for you. So again, let's just kind of look at the, let's look at the sine graph here. So let's talk about amplitude. So the amplitude again is this half distance between the max and the min. Okay, so it's important because it's not the distance between the max and the min, but it's basically the half distance. And the period, how long it repeats itself. I guess actually I don't really need to do any examples here. I mean, I could write out what amplitude and represents, but I probably should type that out rather than writing it with this. So I think that's good. I think we cover the initial period, and with these, I think that'll be good. Actually, I guess I could, let's kind of continue this graph on. So actually, let's kind of look at this. So what you can see here is the graph here, from here to here to here is 2 pi, right? Well, again, you can see that the graph is again going to repeat in another 2 pi. And if I was actually to do this again, you can see this graph is again repeating in a 2 pi. So that's what we call the period. is basically how long the graph takes to repeat itself. And then this half distance is basically going to be the half distance from the max to the min is going to be our amplitude. Okay, it's just very important to make sure that you're careful with that amplitude. Don't treat it as like the max to like the X-Intercept, because obviously the graph can be shifted up or down. So it's just that half distance from the max and to the min. And then obviously the phase shifts are going to be moving. You can see that the graph is the range. It has a max and min. That's why I'm using brackets. Whereas the domain, it just continues on and on forever. So therefore, that's why there is parentheses there. All right, but let's go and talk about the tangent function here, because I haven't talked about that yet. So if you were to go ahead and tangent function. Oh, initial function. I meant to say initial period. So the initial period of the tangent function looks really, really cool. So it actually has asymptotes, which we have not discussed yet. So if I remember this correctly, it's going to look like that. Let's redo that. So it kind of has like that S-curve shape that most students are kind of familiar with, like the cubic. It's not the same, but it's important. Now, the reason why we have these asymptotes is, let's go and look at that initial period back on, let's see, let's go and look at the initial period. Does it actually work on this one? Can I use any function here? Let me see. I don't know. Construction of the sine curve. Yeah, I'm not sure if that's. Okay, I don't know what I'm going to do with that. So let's go ahead with transformations. Let's use the tangent function. Okay, so here's the tangent function. And you can see that we have these undefined values. And as I kind of like zoom out here, you can see this graph just keeps on repeating, right? And I always like to do this with my students, like, whoa, looks really cool, right? Maybe not, but I think it's kind of cool. So as we kind of get nice and closer into there, you can see it's just these nice little S-curves, and they keep on repeating themselves. But the issue is they don't repeat themselves every 2 pi. Now, obviously, I have numbers along this axis instead of radians. But one thing what we look at here is that they actually repeat themselves. Like there's these first asymptotes at negative pi halves and pi halves. And again, actually, let's look at the unit circle to make sense of this. So remember, the tangent is the y coordinate over the x coordinate, right? And what we notice here is at 0 over 1 is 0. And then when we go ahead and work through these, you get the square root of 3 over 3, which is 0.86, and then we get 1, and then we get the square root of 3, which is 1.73, and then we get 1 over 0 for pi halves. And at 1 over 0, you can't divide by 0, so you can see at pi halves it's undefined, and at negative pi halves, the graph is going to be undefined. So therefore, that's where you can see this initial period. And again, this graph is going to repeat itself, right? Just like the sine and cosine graphs. The difference here, though, is the period, instead of it being 2 pi, the period is actually only pi. So the same thing is going to happen, same thing that we kind of talked about before here. However, if you want to find the start and the end, what I like to do is, if I want to find the initial period like the start, what I do is I take negative pi halves. Oops, I'm sorry. You want to set whatever's inside of your function, which was the exact same that we did before, the b theta minus c. So we'll do b times theta minus c. And then set that equal to negative pi halves. And then to find the end, we're going to take b theta minus c, and then equal that to positive pi halves. So therefore, what you can do is you can see the difference. Now, again, this is when you have a b and a c. A lot of times, if you just know what the c is, like a c is 1 or pi, then you know like where the graph got transferred, shifted. But sometimes it's not as easy as that. So that's why we're going to use, instead of the start and the ends being at 0 and 2 pi, like I did before, right? Now you can see the start and end of the initial period is at negative pi halves and pi halves. And again, let's just like expand on this. Let's do just a couple periods in both ways. So that'd be negative pi halves, pi halves. So you can see the graph would look like that. And again, if I was going to since it's moving a period, what's nice about this is if here's the x-intercept, the next x-intercept is going to be a period to the right, which in this case would be pi, right? Pi units to the right. I know my next intercept here is going to be negative pi. And then pi plus an extra period plus pi halves is going to give me at 3 pi halves. So I can kind of like get an idea now of where my asymptotes are because everything is a pi away from each other. That is, again, for the initial period. Obviously, that changes or can change when we have a change in our period, right? And again, our period can change based on the value of b. So to find the period change, we're going to take pi and divide it by b, which is similar to sine and cosine, except it's pi instead of 2 pi. The phase shift and vertical shift, those are basically going to be the exact same things. Just remember when you have a c and a b, that's where you want to use the start and the end to identify those shifts. The domain is where we get really kind of confusing because it's basically all real values except for where these asymptotes occur. So a great way to understand where the asymptotes occur is to use this equation, x equals pi halves times n. And again, just think about if n is 0, that's not right. That's pi halves and plus pi halves. That's at 0. We don't have an x-intercept at 0. That is incorrect. We have an x-intercept at pi halves, and that's going to be plus pi halves. There you go. So if n is 0, then we have an intercept at pi halves, right? And actually, that's not going to be right either. I'm going to have to go back to my drawing board. That's wrong. Sorry about that. But what you can see for each one of these intervals, as I keep on adding, each intercept, that's going to be at pi. So there we go. Let me see what I get here. It's not going to be at 0. I fixed it. I figured something ahead. It's going to be pi halves plus pi. There we go. Because we don't ever want to, we're not ever going to want to get to 0. No, it's pi halves plus pi n. There we go. That's it. So x is equal to pi halves plus pi n. That's wrong. Okay. That's it. So when n is equal to 0, we have an asymptote at pi halves. When n is equal to -1, we would have an asymptote at negative pi halves. When n is equal to 2 or 3, you can see that when n is equal to 2, or let's say 1, then we'd have pi plus pi halves, which is at 3 pi halves. And if that was -1 or -2, you would have -3 pi halves. So therefore, you can kind of see how this works. As far as the x scale, you can still use an x scale of 4. I don't like to use 4 because I don't really consider these points on tangent to be critical points or points that are much value. They help you graph it, but I kind of know the shape of the curve, and that's really mostly what I expect. So I just use usually only just an x scale of 2, basically because I want to know where's the intercept and where's the x-intercept. And obviously, if I needed to actually get a good graph, I would just use a graphing calculator because there's enough things to worry about tangent than trying to like get the vertical stretch or compression exactly correct. So either way, hopefully that kind of helps you out at least understanding the tangent graph as well as our characteristics for the sine and cosine graph. So now the time is to get on to some examples. Let's go.